Okay, let's start my presentation here. It is my honor to be here to do the presentation, although this is the first time I joined OCP Summit. My name is Gregary Liu, and I'm responsible for the product planning in Wiwynn. Today, my topic is to leverage the OCP design advantages on EIA 19 accelerator server. Okay, this is this product. We are not going to limit it to only a GPU or FPGA cards, but we want to push it to the high performance computing field. So we use the accelerator server. First, I will go through my agenda today. First step, I will give you a brief system overview of our system so that you are aware of the design we are doing now, and we are going to contribute this product to OCP in Q2 this year. Second, I will give you a brief introduction of the high CFM per watt thermal efficiency of this system, which is really the highlight of this system design. Next, I will give you the flexible and easy design for different applications, how we can achieve them, and how you can easily migrate into different application scenarios. Then it will be the design for serviceability of this system. And next, we will talk about the design extension to ORV2. And last but not least, we'll talk about the power distribution design for ORV2. This is important because, as we know, OpenRack mainly uses 12-volt DC to supply the system power. And at this high power consumption system, the current will be very, very high. So the way we give a good design quality, I will mention that in the following slides. Okay, first we are talking about the system overview. What is this system? This system design advantages. First, we are talking about the high CFM per watt thermal design for large-scale simulation models and deep learning training for all workloads. Next is that by selecting different PCIe topologies and PCIe cards that you can address your applications with different combinations. Next is the OCP-related design highlight. First is the from I/O access, so that all the most of the operation on the I/Os will be on the core I/O, so that the operator will have a better environment for all the maintenance. Next is the toolless mechanical design for labor saving. I will show more detail in the following slides. Okay. Next is that we integrated the field-proven Mount Olympus motherboard in this system for quality assurances, so that it will make you more easier to adapt this system in your environment. Next is the EIA 19 design highlight. First is that this is a standard 4RU system, a high-power server system design. Next, it's designed for 8 double-width PCIe Gen 3x16 slots, which you can use for different workloads with various accelerators in the field. It is a dual-zone cooling design, so that the cold air can run through the PCIe cards directly And the benefit I will show you later on. Next is we use the CRPS PSU to get the 2+2 power redundancy to provide the system stability of the design. Next is a scalable design, which we can easily migrate to ORV2 of this design. And as you can see that I put the picture at the right top side of this slide that this is a short illustration of our system. And this is how do we achieve all these features above I mentioned. It is the accelerator server to achieve them. So what is the basic of this system? First, let's start with the Mount Olympus motherboard here, which most of us know that this is designed and field proven and wide accepted for the time being. And with the help of the PCIe riser cards, we connect the PCIe signal to the switch ICs on the switch board here, which can support up to 8 double width PCIe cards. And the whole system will be supported by the 2+2 power redundant design here. And the thermal efficiency will be guaranteed by the 3+1 redundant system fan design. And last but not least, we can reserve 1 to 2 PCIe slots for the system to connect to outside world, which means that you can use NIC cards or kind of PCIe retimer card again to connect to outside for your applications. Next, we will talk about the high CFM per watt thermal efficiency. Okay, this system is designed to isolate the thermal cooling zones, enable cold air to run through the PCIe cards directly. As we can see from the top picture here that the cold air will be separated by the interface here. Okay, the top zone cold air will run through the system inlet to the PCIe cards directly. Although there is the hard drive or SSD in between, they will not contribute too much heat to the air. So I will show you more testing results later on. And the cold air will go through the PCIe cards directly and being exhausted by the system fan. And for the cold air at the button U, it will be guided through the motherboard to cool the CPU and the memory, then being guided to just in front of the system fan, then be moved upward to upper U, then be sucked out of the system. So this design will make that the air here will not impact the cooling of the PCIe cards and the PSU. As for the air going through the button U, it will be evenly distributed first when they get in the system, and then be guided and concentrated to the center and right before the system fan, and will be pulled out of the system at the upper U. So this will result in very good thermal efficiency. How good is it? I should share you with some more information. The number is better. Okay, so the thermal efficiency of this system will be, we can reach 0.135 CFM per watt at 30 degrees Celsius ambient temperature. And even we can reach 0.117 CFM per watt at 25 degrees C. So according to the data we collect so far, that our measurement, our real test data will exceed most hyperscale data center requirement. So especially at this time that we all talk about the TCO for data centers, this will be very good benefit for the customers who adopt this system. Next, with this high efficiency thermal design, we can achieve 3+1 system fan redundant design for up to 2.8 kilowatt at 35 degrees C. The data I'm showing later on is at the one fan fail condition. If all the system fans are working properly, the efficiency is much better. Okay, so when we are at the 35 degrees C inlet temperature for the ambient temperature, and when one fan was failed at this location, the system thermal test data is shown as here, that the inlet temperature of to the PCIe card would be 35.3 Celsius. You can see that the temperature difference is not much or even equal. And after the PCIe cards, the test data we test with NVIDIA V100 card here, that the PCIe outlet temperature will be 52.5 degrees C. So it's only 70 degrees differences. And the system output outlet temperature is 48 degrees C. So this is how we made this at even one fan fail condition and high ambient temperature environment. Okay, next is the flexible and easy design for different applications. Okay, this I will separate into two parts. For different applications, you have different requirements in terms of the CPU to PCIe cards ratio. For the first topology we provide is that we call it balance mode, that the CPU to GPU ratio is 1:4. The way we achieve that is like we use the two-socket motherboard here, and our switch board design is like this. 2 switch ICs each connect to 4 GPU cards separately, and with the link of the cable. With the link of the cable from one CPU to one switch IC directly, that one CPU can connect to up to 4 GPU cards directly. So at this balance mode, that we will get higher bandwidth in between CPU and the PCIe cards. This is good for your applications when you are using more CPU computing power compared to other models. Next is another topology that we call the cascade mode. Under this mode, the CPU to GPU ratio will be 1:8, which means that CPU 0 will connect to all GPUs via the link of 2 PCIe switch ICs. And under this condition that the peer-to-peer performance will be much better in between these A cars compared to the other mode. So it depends on your application need that which topology you should adopt it. But the point for our system is that we design the connection with the cables so that you can just reroute the cables very easily. Actually, only one cable is needed to be rerouted. Reroute the cables so that you can achieve your requirement or your demand on the system topology. So it is very easy and really flexible for your application. So next is design for serviceability. For this part, we have two parts for PCIe cards serviceability design. First is we modularized the toolless design for the PCIe, the switchboard tray. As the system ISO view shown here that we can remove the whole switchboard tray outside of the system so that it's easy for you to do any maintenance or even the initial installation of the double width PCIe card. And we did one step further that we used the quarter turn fastener for the PCIe cards so that not only good for the PCIe cards replacement, but it is also good for the initial installation of the cards. It is real fast and make your operation more efficiency. Next is that our design for the rotatable SSD bracket for PCIe card maintenance on the motherboard, on the Olympus motherboard. When we remove the top cover of the system, we will look like this. And this is the SSD bracket I mentioned. It is designed rotatable that when you rotate it upward 90 degrees, you can do all the maintenance on the motherboard, although it is at the bottom U of the system, that you can remove the PCIe cards easily, or you can also do maintenance on the CPU and the memory on the motherboard. So it is completely toolless design and also prevent any interference to serviceability on everything on the motherboard. Next is the design for fan and SSD replacement. We modularized our design so that you can remove our system fan easily, and it is a labor-saving handle here that the operation is very easy and quick. And of course, the SSD is designed with the bracket that it is support hot swappable feature. Next is the design extension to ORV2. For our initial design, we make it possible to retrofit the design to ORV2 and adapt to 12-volt DC power bus bar. Next is that we design the PTB for power transition to provide power to the motherboard and the PCIe switchboard, which I will show more detail in the following slide. And with the more space we get from 21-inch rack, that we increase the SSD number to 8 for this system. And the detailed spec is listed here. Okay. And last will be the power distribution design for RV2. We use dual bus bar clips to support this system to up to 2.8 kilowatt, as you can see from here. And for the power supply to the whole system will like this. Clip 1 will support fully to the switchboard directly, while the other clips will support to switchboard, motherboard, and fan board simultaneously, so that we can make this system in good condition. Okay, so this is my presentation today, and we do have this system in our booth. And if you are interested in our system, you can come over to have a look at our systems. Okay. If you have any questions, please, you may start to ask. Okay. If you have any interest in our system, please move to booth A12, and we can have a discussion in person. Okay. Thank you.